Okay. Ladies and gentlemen, this is Liana. I'm actually not one of the authors. I'm here on behalf of Zhou Yu to deliver this talk on improving VQA performance with mixture of detectors features. As we know, the general framework for existing VQA approaches may consist of the following three parts. First, feature level. On feature level, feature representation model pre-processes the question and image into textual and visual features respectively. And the second level is the model level. Multimodal features are integrated together into one feature vector. Usually, attention mechanism is imposed on visual features and textual features. And the third level is loss level. The fused features are fed into a classifier to predict the answers. In previous state-of-the-art approaches, there are some commonly used implementations for the three key components of the framework. For feature representation, LSTM is usually used to represent questions, and concatenating with a 300-dimensional globe feature is an effective enhancement. Bottom-up attention visual features is also widely adopted. When fusing multimodal features, co-attention mechanism, combining visual and question attentions can be more reliable than both of the two alone. Among various fusion strategies, MFB and MFH stands out in practice. For answering modeling, multilevel KLD is a competitive choice. By integrating the state-of-the-art implementations together, we have the model shown as follows. We regard this as our reference model. Question attention, first, question attention is fed into visual attention learning. Double glimpses of question attention and visual attention are learned and concatenated to get complementary information. Here in the graph, there is only one glimpse of question attention, but actually it's two. This is a small imperfection. We report the overall accuracy of 68.76%, which is a very competitive model. The details of the model and MFH can be found in our paper shown on the bottom, and the codes are also released. Treating our reference model as a baseline, we want to have further improvements. From previous experiences, we have the inspiration that the representation capacity of visual feature is the bottleneck of the VQA problem. Although the bottom-up attention features is good, its backbone network is already not the state-of-the-art now. In our initial solution, we have a simple idea to replace the fast RCN model with another stronger detection model, for example, FPN with ResNet 152. To accomplish this, we migrate the original Café project to Detectron project and train on FPN with ResNet 152 model on visual genome dataset. However, for some reason, actually we are still debugging, the output feature from the FPN model is not as competitive as the original fast RCN features. At this point, we only have 1 week of time before the final challenge deadline, so which is not enough for training another model. So we think now we have two object detection models. Can we combine them together to obtain more powerful visual features? Directly combining the features from different detectors is not an option because they are not actually aligned. To this point, we propose a simple mixture of detectors strategy. First, we use one model to generate the bounding boxes. And based on the bounding boxes, two different models extract bottom-up attention features using fast RCN-like strategy in parallel. Now the features are well aligned, so we can easily concatenate them. We call this feature MOD feature. Here are the details of our MOD features. It's a 3072-dimensional feature. Note that during bounding box generation, we have two options on the number of output. The first one is dynamically determine the number of output bounding boxes, which is used in the original bottom-up attention. They set a lower bound of confidence threshold and choose 10 to 100 bounding boxes for one image. We tried another strategy that to generate fixed number of bounding boxes, in our case, 100. This brings a little more storage and computational cost, but also brings some performance improvement. Our experimental results for a single model is demonstrated as follows. The table shows the results of using the MOD feature comparing with one using the original bottom-up attention, as well as the performance difference of using fixed K and dynamic K. From the reported results, we can see that MOD brings 0.71% improvement over the reference model with dynamic K. And using fixed K brings about 0.35% improvement over dynamic K for MOD features. But one thing we should notice is that for number type, the performance is even lower than the reference model. This may be because fixed K brings about repeated count on the same object. Okay, this table shows the results of model ensemble. We train 12 independent models and average their predictions with equal weight for each model. The variables for each model is the number of glimpses, the fusion strategy, and whether involving additional VQA samples from visual genome into training set. Note that for more diverse ensemble, we additionally combine 4 models with a visual feature extracted with dynamic number of bounding boxes is the last 4. This figure shows the performance along with the ensemble of different number of models. For single model to 8 models, the performance has 1.2% improvement, and the performance seems approaching a saturation. However, by introducing another 4 models with different features, it has another 0.7% of improvement, which proves the importance of diverse models and features. On the right is the performance of our submission with 12 models. On TestDev, our performance is 71.75 and 72.09 on test standard. We visualize some examples on different types of answers to show the difference between using dynamic K and fixed K. Larger K tends to discover more details of the image, which makes its performance on yes or no type and other type better. This is an example on yes or no type. The fence on the corner and the wood pile are the key to answer this question. For number type, larger K leads to redundant bounding boxes for one object, which makes it harder to learn correct visual attention. There are some works dig up to counting the objects due to time limit and small percentage of this type takes. We just didn't involve this into our model. Now we reach some conclusions. First, visual features are still the key to VQA problems. And second, MOD features can improve VQA performance even against a strong reference model. And third, fixed K is better than dynamic K on the overall accuracy, but actually they have their own advantages on different types of questions. And fourth, model ensemble is important to further boost the performances. And those are the conclusions we reach. At last, we give special thanks to the VQA Challenge organizers and Peter for releasing the bottom-up attention codes and models, and FAIR to releasing the Detectron project. You can find our papers and codes from the following links. Thank you very much for listening. Any questions?
Thanks a lot, Liana. Questions?
Okay.
No questions? Okay, this one.
Short questions. Are you planning to present, to write some paper about this, technical report or some paper?
That's out of my knowledge.
Okay.
Because I'm not one of the authors, but I'm sure if you send an email or something like that.
Thank you very much.
Any other question?
Are we good?
Thanks again.